Imagine your centuries-old encryption suddenly becoming vulnerable overnight. Classic ciphers, like RSA or AES, rely on mathematical problems that take traditional computers ages to solve. But with quantum cryptography, this security assumption shatters. Here is a concrete example. Shor's algorithm can factor large numbers in polynomial time, something classical algorithms cannot do efficiently. That means the public keys protecting your data can be cracked far faster than anyone suspected. Let us walk through how Shor's algorithm breaks RSA. Start with the RSA public key, which is a product of two large primes. Classical factoring algorithms struggle because the complexity grows exponentially with key size. Quantum computers run Shor's algorithm to find the period of a function linked to the key quickly, identifying the prime factors. With those, the RSA private key is instantly recovered. This is why a 2048-bit RSA key is not safe from a sufficiently powerful quantum attack anymore. Here is a mini walkthrough. Suppose you intercepted an RSA encrypted message. First, find the modulus n, the product of two hidden primes. Classically, factoring this 2048-bit n is beyond feasible, but with a quantum computer, you run Shor's algorithm to discover the period function needed to find those primes. Once those primes are found, decrypting the message becomes trivial. The key step is how the quantum Fourier transform accelerates the period finding process. A common mistake is assuming only RSA is vulnerable. AES, built on symmetric keys, is still partially resistant, but also threatened. Grover's algorithm can quadratically speed up brute forcing AES keys. That means AES 128 effectively becomes as secure as a 64-bit key against quantum adversaries. The practical takeaway: doubling AES key length to 256 bits helps maintain security margins against quantum attacks. Now let us contrast quantum attacks with classic brute force. Traditional brute forcing high-bit keys is impossible within realistic timeframes. For example, a 128-bit symmetric key would require 2 to the 128th attempts. Grover's algorithm halves the exponent, making 2 to the 64th attempts necessary, a huge reduction, but still quite large. This nuance means quantum computers challenge, but do not instantly break symmetric ciphers, highlighting which ciphers need upgrading first. Here is a practical rule of thumb. Whenever your encryption depends on factoring or discrete logarithms, like in RSA or Diffie-Hellman, it is vulnerable to immediate quantum attacks using Shor's algorithm. For symmetric ciphers, assume Grover's algorithm halves your effective key strength. To prepare, move to quantum-resistant algorithms like lattice-based or hash-based cryptography. This decision is not theoretical. It impacts everyday security in communication, finance, and government data. Understanding how quantum cryptography breaks classic ciphers gives us a roadmap. 1. Recognize the fundamental weaknesses, factoring and discrete logs. 2. See exactly how Shor's and Grover's algorithms exploit these weaknesses in concrete steps. 3. Apply quantum-resistant protocols and lengthen symmetric keys accordingly. This concrete takeaway arms you with a practical security mindset to navigate the quantum future confidently. This is just one small part of technology computing future tech, still concrete enough for Quizz's Quantum Computing What? A full free technology computing future tech, still concrete enough for Quizz's Quantum Computing What course is linked in the description, with more than 100 subtopics.